related to numerical integration. So if you recall, we are in module 4, which involves numerical differentiation, which we have been seeing in the last 2 lectures. And today we are going to look at numerical integration. Now, before we walk into integration, you already know that you have this entire theme is about what? You have data, say x and y equal to f of x. You have data at x1, y1, x2, y2, x3, y3, and so on, xn, yn. Now you know the processes. Like for example, if I ask you to fit a curve, that process is called regression. So you try to come up with y fit, which is a good estimate for the function, which is underlying the data. Number 2, if we want to interpolate or interpolation of values between the points provided, that is interpolation, just to keep it in perspective for you. Now, if you have the same data set, computing derivatives, like for example, you want to get f dashed of x, f double dashed of x, and so on. We saw different ways of computing the derivatives. Just sort of like a recap of what we have done so far before I start the next topic. So we talked about a grid point I, which we'll call as current. There is I plus 1 next, and then I minus 1 behind, or we call it previous. So we have different types of approximation: forward differencing, central differencing, and backward differencing. So we might be trying to approximate a derivative of a certain order, like first derivative, second derivative, third derivative, whatever, using, see, that's the flu shot that I asked you to take. It could also be allergies. So it could be forward differencing, central or backward differencing, which is usually dictated by the physics in hand. So you can't just arbitrarily choose one of these. It has to come somewhat grounded on the context. And then once you do this, how many neighbors do you involve? How many neighbors are involved? You could have just the immediate neighbor, or one neighbor once removed or twice removed, and so on. So how many neighbors are removed, and what is the order of magnitude of the error in this computation? So usually these are the key aspects of computing a derivative, and for doing problems both for the homework and for the exam, you have to refer to figures 23.1, 23.2, and 23.3, which are formulas for various derivatives in forward, central, and backward differencing involving many neighbors. And the starting point for all these formulas is Taylor series. Without Taylor series, or without knowing what it is, you can't make sense of those formulas. So this is a short recap of numerical differentiation. And now, the fourth operation we are studying on a set of data is numerical integration. Yes, thank you for the reminder. I am recording, luckily. So if you plot the data, you have say a bunch of points. Differentiation is all about getting the slope or the curvature at any given point. So if this is your point of interest, getting the local slope or curvature or any higher order derivatives like third derivative, fourth derivative, and so on. That is the process of differentiation. Integration, on the other hand, I'm sure you have seen this in your calculus courses. Can you tell me what integration geometrically means and what physically it means? For the 42nd time, can you please be louder?
Sorry,
Yeah.
it means the area under the curve.
Area under the curve. So if you have a bunch of points, so if this is your region of interest, it's literally the area under the curve, which we compute as an integral. So if you write x1 or xa to xb, f of x dx, this is nothing but area under the curve. That's easy to state. Okay, now we'll talk about some applications. Where do you use this concept of area under the curve to figure out stuff or to calculate quantity? Can you give me examples where we use integrals to evaluate something that we care about?
Like power output from a certain.
Good, power output. What power is the integral of which quantity and which quantity? Voltage and current. So, okay. So if I have data where I have the current and voltage, and if they have a certain relationship, you are saying that the power dissipated in the circuit is either V di integral, or it can also be integral I dv, depending on how the data is presented. Okay, any mechanical engineering or mechanical related examples of where you use integrals to compute quantities?
Finding acceleration of parts in the machine.
Finding the acceleration. So acceleration is typically the second derivative of position or the first derivative of velocity. So is your goal to find acceleration?
Would be use that to find velocity of parts.
Okay, so I'm going to take that and turn that into like a word problem. Suppose you are riding your car from say Memphis along a route. You just don't keep track of which routes you're taking, and you're just the only thing you record or your car records is your instantaneous speed as a function of time. And to keep it sort of little less cluttered conceptually, suppose you are heading north on I-55 and your instantaneous speed, let's say you are all nice and polite drivers, right? I wouldn't think otherwise. Then you keep it around 55 miles per hour if the speed limit is that, and you stay there. And except when you have to get out of the freeway, maybe get coffee, you drop it down, you come to rest. For some time you are having your coffee and then coming back, and then you catch up on the freeway. And let's say you do this for about 4 hours. How will you estimate the total distance driven? Distance is nothing but speed multiplied by time, or average speed multiplied by time. How would you get the average speed when you were, let's say when you started from your home, there was some time where you have to ride in like a 40 mile per hour zone, and then you entered the freeway, and this is your speedometer reading versus time. So how will you compute the total distance traveled?
Integral
Integral of what?
of the velocity function, and the bounds would be the time.
So 0 to whatever time here, I'll call this uppercase T. So he's saying he'll integrate from 0, time equal to 0 hours, to time equals to uppercase T hours of the speed multiplied by dt. This is just like going back to your mechanics class, where distance traveled equal to speed multiplied by time, but only change is the speed is a function of time itself, because as you accelerate and decelerate, it keeps changing. How do you actually carry out the calculation? If you are taking your sensor and hacking it to print out the values, it's going to look like time as a column and velocity in miles per hour, say time in hours. So maybe time in minutes, and velocity in miles per hour. So 0, 0, and then some values up to 4 hours. Yes.
If there were a single function that defined the entire segment, then
Stop. No functions, only data.
then you could use geometric analysis, so you could split.
What is geometric analysis? See, if you are explaining something, you should use less dense terms than what you're trying to explain.
So you could split the plot that you have into shapes
Okay.
that you can easily calculate the area of. And once you add up the area of all the shapes, that should.
All right. All right, I get what you're saying. So you want to say that this is like a rectangle where the speed was nearly constant, and this is like a triangle, and this looks like a triangle, but there is a curvature here, so it'll be weird to call this shape a triangle. Okay, and then there was some time when there was nothing, there is no area, no distance traveled. You were idling your car at the Love's parking lot, sipping your coffee. So how do you do this systematically? All this is just patchwork. You are not giving a solution.
Are you gonna say piecewise solutions?
We don't want to do piecewise curve fitting. What we want to do is, if you take, say for example, this portion of the curve, where your speed went from 0 to 55 miles per hour, let's say, how do we split this and integrate it? That is, you want to get the area under this curve, which you know this is V of t and this is t. So you know very well that what the quantity you are trying to calculate is this, from 0 to maybe this is like 1 hour. So 1 hour. So the way you do that conceptually is, this is a curve with significant curvature. But if you keep splitting this into fragments, smaller and smaller fragments, I can divide this into smaller and smaller fragments. And if I take a small enough fragment, this side is just your delta t, and this side is, I'm going to magnify this and draw it here. So here is, say for example, 65 minutes, I'm sorry, like 35 minutes, and here is 30 minutes. So this delta t is 5 minutes. So at this point, I have the velocity of the speed here. Okay, so this segment is what I'm kind of magnifying and drawing here. Say suppose this is 45 miles per hour, and this is 37 miles per hour. This is delta t. I'm going to make an approximation that I'm going to draw a straight line connecting these 2 points. So what is the shape I have now, where there are 4 straight lines and one of the sides is perpendicular to the other, and the other is not necessarily perpendicular. What is the name of this shape? This is the trapezoid, and the process of segmenting your domain into small finely divided trapezoids is called the trapezoidal rule. Okay, so we are trying to, step one, divide the interval of integration into fine fragments or intervals such that each fragment can be approximated as a trapezoid, and from your geometry, what is the area of a trapezium? Area of a trapezium.
I always forget, I always do a triangle and a rectangle.
Yeah, you can do that and tell me. It's actually half the height multiplied by sum of parallel sides. As I write that, I'm astonished by the fact that I learned this in 5th or 6th grade and I still can write it. This is what my math teacher literally said. Half times height multiplied by sum of parallel sides. Okay, that's good. So what is the sum of the parallel sides? Okay, first of all, what is the height? This is the height. This is your height. Okay, that is your delta t or delta h or delta x, whatever you call it. And then what is the sum of the parallel sides? It is the value of the function at, say, t2. So this is v of t2. And then the value of the function at t1. So this is v of t1 plus v of t2. This would be the distance traveled in the interval t2 minus t1. Give you time to write this. Okay, so if you have written this, answer these questions for me. When does this approximation actually become the true answer? That is, suppose you take this example, if you are interested in the distance traveled in this segment, where you are coasting along in the freeway, the traffic is all steady, the speed's not changing, maybe you had your car on cruise control, and this was 55 miles per hour, which you did for like say 45 minutes. So it's easy for you to think what is the distance traveled in that time, right? Because it's like saying the VT1 and VT2 are really the same. It's getting the area of a rectangle there. The rectangle being this. So now tell me, when is the case when the trapezoid rule becomes exact?
If you have an infinite amount of trapezoids. If you have an infinite amount of trapezoids.
No, it becomes exact when the value of the function that you're trying to, remember, you are always trying to integrate this. So if this is going to be from 0 to 4 hours, okay, this is going to be from 0 to 4 hours. For the first 45 minutes, you are going through, accelerations and decelerations, whatever. But the next 45 minutes has been at steady speed. So if I split this, this is going to be 0 to 45 minutes of v of t dt, plus then 45 minutes to 90 minutes in which my speed was constant, so that speed was 55 miles per hour dt. So your trapezoid rule, the approximation which we get by dividing the interval into finely, made trapeziums, it becomes exact if the value that you're trying to integrate is really a constant. If you are trying to integrate v of v dt, if this is equal to v constant times dt, then it's simply v constant times delta t. So you can see that it becomes exact in the limit when the function you're trying to integrate is just a constant. When does it get worse, or when are the reasons where possibly this can be bad? Suppose you consider this segment here. Suppose you consider this segment. No need to write now, please don't write now, and then I might say something that's important. I'll give you time. Suppose you are considering this segment here, and if you are dividing the whole thing into just one trapezium. So here is the starting point, and here is the ending point of the trapezium. So it's like saying v of t1 is 0 and v of t2 is 55 miles per hour, and delta t being, let's say this is like 20 minutes. It's like saying my trapezium is really a triangle here, which, if I compute the area according to this formula, the area would be everything that is within this straight line. This portion here, between the dashed line and the straight line, this is the error. Do you see that concept? Do you see that if you make a very crude trapezium, you can get significant error? And if it happens that your function is not changing at all, or if it is changing at a very specific steady value or a linear rate, the error is almost vanishing, or not almost, the error vanishes. The error gets worse as the curvature of your function becomes higher. That is, if you have a second order curve or an exponential curve or a trigonometric curve, the error compounds and adds up pretty quickly. So, what was your question?
I was gonna say, wouldn't or you already answered it, but
Okay.
the trapezium method would still be accurate for a linear function, right?
It will be. The trapezium will still be accurate for a perfectly linear function, simply because if you take a linear, suppose this is the curve, and you want to compute the area under the curve, it naturally is a trapezium. So it doesn't matter if you don't finely segment it. If you just take the entire interval, you would still have the same value, regardless of whether doing it this way or doing it as the entire interval. So the key point is for constant functions and linear functions, the trapezium rule gives you exact value or exact value of the integral. For functions that involve significant curvature, that is, wherever you have dv of dt or d squared v over dt squared being significant, then you are having significant error. How will you overcome that error? How do you kind of mitigate that possibility? Yes.
You could decrease your interval size.
Okay. How?
Well, you decrease 20 to like 10, you double the amount of.
Okay. So you have to increase the number of intervals, but when you do that, you also have to estimate the error that you accumulate in that process. So what I'm going to give you is formulas that will allow you to evaluate any integral or any integral of any data set provided to you, and also an estimate for the error that comes with it. Okay, so we're going to see a couple of formulas which you should use. Basically, if we give you a table of data and ask you to compute the integral, that's the formula you're going to use, and an error estimate for that formula. Okay. So this is all just to motivate the discussion. I'll give you the formula in a easy to read form, okay? So this is section 23 or 21.1. So let me erase this. So trapezoidal rule. We are trying to evaluate I equal to integral a to b f of x dx. That's the integral you want to solve. And we are going to try a specific example. Let's say we get 1 plus x squared or 1 over 1 plus x squared. That is our f of x. And we want to integrate this between 0 to 1. A equal to 0, b equal to 1. Even before doing the problem, you can tell me what the answer is. So integral dx 1 plus x squared 0 to 1, what is the answer? This is tangent inverse of x from 0 to 1, which is pi by 4. So we know what the answer is. We are going to use numerical integration to see how close we get to the answer. And if you were to graph the function in the interval 0 to 1, how will it look like? So this is f of x, 1, this is x. At x equal to 0, the function has a value of 1. At x equal to 1, the function has a value of half, so 0.5. Does it have any maxima in between?
It should steadily decrease.
Should steadily decrease, so minus 1 over 1 plus x squared times 2x. So it should always steadily decrease, that's right. Something like this. So you are asked to compute the area between 0 to 1. Zero to 1. Okay. We'll do this step by step. That is step 1. We'll consider the entire interval to be a single trapezium. Step 2, we'll try to split it into three such segments. And step 3, we'll try it with more segments. Okay. So that you will see that as the number of segments increase, your calculation becomes more accurate. So step 1 or pass 1, I shouldn't say step 1, that is misleading. We'll say case 1, where we are going to have single segment. Okay. So remember the trapezium rule, I trapezium or I trap is approximately equal to half multiplied by delta x times f of a plus f of b. Where in our case, delta x is nothing but b minus a. One second. It is like taking the function from 1 to 0.5, 0 and 1. Okay, the actual curve looks like this. The trapezium we are building is just taking these 2 points and joining them by a straight line. So this is 1 unit. This is 1 unit. This is half unit. So the area would be half multiplied by 1 multiplied by 1 plus half. What was your question?
What's the substitute on I?
Trapezium, trap. TRAP. Or that sounds bad. TRAP. So this is 3 halves multiplied by half or 3/4. This is 0.75. What is the exact value of the integral? I exact equal to pi by 4. Pi by 4.
0.7854.
0.7854. Thank you. So you can compute what is the relative error. Relative error epsilon r, which is 1 minus I numerical or I trapezium divided by I exact expressed as a percentage. This is 1 minus 0.75 divided by 0.7854 expressed as a percentage. Can you tell me that?
$4.51%.
4.51%. So this function is moderately nonlinear. Okay, it's not super nonlinear in the sense the slope doesn't change drastically. But if you had a function that looked like this, for example, here is tangent of x. Okay, here is 0, here is pi by 2. What is tangent of pi by 2? Tangent of pi by 2. Tangent of pi by 2.
It's over 0, so
Infinity.
That's remote.
It blows up at pi by 2. I think you guys you know the answer, you're just shy or you're not sure. You just have to take a call. You can either be wrong or right. That's the big deal. Okay. So tangent of pi by 2 is infinity. So if you are trying to compute, say for example, pi by 4 to pi by 2 of tangent of x, of course, you can't do exactly pi by 2, so we'll do pi by 4 plus pi by 8. What is that? 3 pi by 8, 3/8. If you are trying to evaluate this integral, it would come somewhere here. So here is pi by 4, here is halfway between pi by 4 and pi by 2. Look at how strong the curvature is in this interval. So if you apply the same method for this portion of the curve, it would be half multiplied by the width, which is pi by 8, multiplied by tangent of pi by 4 plus tangent of 3 pi by 8. I'm trying to make the point that when the curvature becomes steep, this approximation gets that much bad. So what do we do now? We have 4% error. Your goal is to reduce that error. What would you do? See some tired faces. Is it because it's not making sense? Can you tell me what the issue is? What would be the next step here? Divide into more segments, so let's try doing it into two segments. So we'll try to split this as 0 to half and then half to 1. So we want to split this into two trapezia, where you have the first one running from 0 to half and the second running from half to 1. Okay, so in that case, can we compute what happens? Can you try computing two values of the integral for each of the segments and then trying to add them? So I will call this I1 equal to 0 to half f of x dx, and then I2 equal to half to 1 f of x dx, which is approximately equal to half. What is the width of the interval here? From when you go from 0 to half, what is the width of the interval? B minus a, half minus 0. So multiplied by half minus 0, and then what is whatever is f of 0 plus f of half. So if you compute this, this is half multiplied by half. What is f of 0? 1. And what is f of half? Did I hear 0.8? Okay. 0.8. So this is 1.8 divided by 4, which is 0.45. And the second segment, so this area is, estimate is 0.45. The second segment, I have half. What is the width of the interval? B minus a. 1 minus half. 1 minus half multiplied by f of half plus f of 1. So that would again be 1 by 2 times 1 by 2. F of half is 0.8, f of 1 is 0.5. So that's 1.3 divided by 4, which is 0.325. So this is 0.325.
Did we estimate at the 1/2?
That I was told that is 0.8. Yeah, you need to take 1 over 1 plus x squared and substitute x equals half, which would be what? 1 over 1 plus 1 by 4. So that's 4 divided by 5, which is 0.8. That's what I was told. So that's correct. So if you sum up these two areas, I'll write I equals I1 plus I2, which is 0.45 plus 0.325. How much are we getting? 0.775. And the exact value is 0.7854. So can you compute the relative error between these two? So if you write 1 minus 0.775 divided by 0.7854 expressed as a percentage, is that like
1.32%.
1.32%. So I'll give you time to catch up here. So I need a volunteer to summarize what we have done so far. Yes, please.
So we initially took the area of the trapezoid in one segment.
We took the entire range as one segment.
Yeah, we took it as one segment. And that gave us an error of 4.51%, and we wanted to get less error, so we divided it into two segments. And now get an error of 1.32%. Do you do that until you get into your error range that you want?
Until you can keep doing this until the error becomes as small as you want. The key thing here is we applied the same formula when we did the single segment or when we did two segments. We just applied the same formula for each segment. So suppose you divided this interval into 20 segments, you would apply this formula 20 times. Okay, so there is no real magic here on. It is just adding up the values I1 plus I2 plus I3 plus I20 in order to get the entire value of the area under the curve. So it is generally good practice to put more intervals so that you can hope to minimize this error. Okay, so did that make sense to all of you? Because if you have a question now, you need to ask, because this trapezoidal rule is sort of what we will repeatedly apply in many flavors moving on. So we need to be clear about this. Yes.
So when we're trying to figure out how many intervals or how many travelers we want to use, would it be kind of like how for module one, it's like you want an error of this percent and we just keep going essentially until we get done?
Yes and no. Why I say no? Because in this problem, I intentionally chose this function which can be easily integrated. I know the truth to begin with. So this is always not the case. You are usually presented data and you have to compute the integral from the data. You don't know what the true value is. So it is not possible for you to know what the error is in this sense. But there are two things we can do. Nice question, Ben. So there are two things we can do. We have this trapezoidal rule, which we write I equal to half multiplied by b minus a times f of a plus f of b. This is for one segment, and we will apply this, repeat this for n segments. Okay, I'm sort of writing like an interim summary here, one segment. We can do two things. One is you can plot or you can calculate the error associated with trapezoidal rule. I'm going to give you a formula and a very short derivation to get I error, which is going to be a function that you can actually easily calculate. Okay, I'm going to give you the formula. The second is, remember when we did numerical differentiation, we talked about resolution of the data and how the resolution needs to be fine depending on how steeply the data is changing. So if you think about the I value, the integral value that you compute versus number of segments. In the examples that we just did, for I equal to 1 or I equal to 1, the error was 4.5%. For number of segments equal to 2, it quickly dropped to 1.3%. Now you can make the argument, suppose I did 10, the error came down to say 0.5%. And if I did like 100, the error went even down to 0.005%, something like that. At some point, you don't see any benefit for increasing the number of segments. That is when you don't have to, which means you can say between 100 and 1000, there isn't much gain, or between 100 and anything higher, there isn't much gain. So I'm going to stick to 100. This is for a given function f of x, which may be highly nonlinear or maybe moderately nonlinear or might be linear for all you know. If your function is linear, you know the answer going in that you just need only one segment. Because linear functions don't really need you to take care of the segmentation so much. You can sort of think the number of segments loosely scale with the nonlinearity of your data. The highly nonlinear your function is, the more segments you will need to finally resolve it and get the integrals value accurately. That make intuitive sense for you. If you're trying to get like a linear function, just one segment is good enough. If you're trying to get something that is highly nonlinear, then you might have to do more segments. If you're trying to capture the same exponential function in a region where it's not changing or it's changing very slowly, you might be able to get away with one or two. That's the intuition you need to have. Okay. So I told you about, I'll give you the formula for the error associated with the trapezium rule. And you can find this formula in box 21.2 in your, or figure 21.2, whatever they call it, I think they call it box. So the error estimate is minus 1/12 f double dash of zeta f double dash of zeta, okay, multiplied by h cube, where h equal to b minus a and zeta is any number between a and b. You can choose any number between a and b, the interval in which you do the integration, and if you compute the second derivative, your error scales with this function. So it's sort of like a ready-made formula for computing what your error is, and it also scales with the step length to the cube. So the finer you make this, the error will become smaller. I'll rewrite it up there. Maybe people in the back are struggling to see it. So I error associated with the trapezoid rule or trapezium rule is minus 1/12, the second derivative of the function evaluated at zeta multiplied by h cube, where h is equal to length of the interval or length of the segment, and zeta is a number chosen between a and b. So suppose if a is 0 and b is 1, you are free to choose any value between 0 to 1. So you can choose 0.25, 0.75, 0.3, whatever between 0 to 1 is a valid choice. So if you look here, what did I start my discussion with? If you had a function f of x which is constant, you need only one segment, meaning trapezoid rule has zero error because second derivative of a constant function is 0. If you had a linear function also, trapezoid rule is still exact. The second derivative of the linear function also is 0. If you have second or higher order functions, you will have non-zero values of these. And if your function has, or if your resolution is small enough, you can still make this become small by choosing a small delta H. So the moral of the story is the error depends both on the function in hand, the properties of the function in hand, and the resolution that you choose to work with. If you have a highly nonlinear function, you can choose very fine resolution, make h really small, and have more segments to mitigate the error. If you have a function that's only moderately nonlinear, you can get away with even a coarse resolution. That is the implication. Okay. So for your problem solving, you need to know this formula and this formula. This is the value of the integral. This is the associated error for one segment. For one segment. We are going to see a version of this formula when you apply it for n segments, where you take any interval between, say, between a and b, and if you divide this into n segments, we are going to just derive a formula, which you can also kind of use without having to do this manually each time. So this is equation 21.6. I said this is in box 21.2, right? That is in my version, which is 8th edition. In the class which we use on the 7th edition, this is equation 21.6. So try to finish writing. I want to show you an example before, like show you meaning literally show you an example to kind of make my point about how big the error can get when you have highly nonlinear functions. Are we all done writing? Yes. So here is a function, a polynomial, a fifth order polynomial, which is graphed by the blue line. And then if we do a application of trapezoidal rule, if we do a single application of the trapezoidal rule, wherein you consider the interval 0 to 0.8 as a single segment, then the value of the function at 0, you can substitute f of 0. You can also substitute what is the value of 0.8. You can get what is f of 0.8. If you estimate using the trapezoidal rule, half of the width of the interval, that is half of 0.8 plus f of 0 plus f of 0.8, which happens to be equal. That is, in this particular function, f of 0 and f of 0.8 are equal. So the trapezoid really becomes like a rectangle. You would think the value of the integral is the area of this rectangle, whereas the function took an excursion, it went up, it flatlined, it reached the peak, and then it came down fast to back this value. It's like taking only two observations, one at the starting point and one at the ending point, and trying to approximate what happened in between. Anything could have happened. It might have increased, decreased, reached the peak, whatever. But the error that you accrue is really shown here clearly, where the true area is whatever is under the blue curve. The one under the rectangle is what you think it is, and the difference being the error. So the solution to these type of situations is you have to have as many number of segments as you can, so that you don't see if you think that if you take this point and draw a horizontal line, you take another point, these 2 points have the same value, but that doesn't mean that the function doesn't do anything in between. That's exactly this example. Okay, so moral of the story, try to have as many segments as you can to get better accuracy. Okay. So how do you do the or how do you get the formula for the integral value when you have multiple segments? That is, if you just thought of it generally, say for example, you have a function, you have a, that is x equal to a, and then x equal to b, and you choose to do this at two segments. So the midpoint of this would be a plus b over 2. Without using any numbers, can you derive the formula for the I1 plus I2? I1 plus I2. Can you do that? Apply the trapezoidal rule twice and get me a formula in terms of the symbols A, B, and f of A and f of B. You want to compute I equal to A to B f of x dx, which we are approximating as I1 plus I2.
Are you asking us to go with f of x?
Keep the symbol f of x. I want you to come up with a formula for I. Assume that f of x is known. So what is I1?
Which is the interval bounds from a to a plus b over 2.
It would be a to a plus b over 2, correct? So I1 is a to a plus b over 2 of f of x dx, which you can write using trapezoidal rule as half of, what is this? This is b minus a over 2 multiplied by f of a plus f of a plus b over 2. Would you agree? This is just the formula for trapezoidal rule applied to the first segment. What would be I2? I2 is a plus b over 2 to b f of x dx, which according to trapezoidal rule is half of, again, b minus a over 2 multiplied by f of a plus b over 2 plus f of a plus f of b. Stare at this and tell me if you have any questions. Somebody had a question.
What do we call it?
Call what?
What do we call it? This I2.
I2.
But then we can do function.
We'll call it the Lie integral. It doesn't have a name, it's just I1 plus I2. So if I want to get I, which is the sum of the two segments, okay, I would just sum up I equal to I1 plus I2, and if you do a little bit of algebra, then it's half of b minus a over 2 common multiplied by f of a plus 2 times f of a plus b over 2 plus f of b. I'm just adding these two. Just make sure you understood where this b minus a over 2 came from. That is a plus b over 2 minus a, or b minus a plus b over 2. It's this distance there, really. B minus a over 2, b minus a over 2. So we have the formula for we have an approximation for the integral a to b f of x dx, which is half multiplied by b minus a divided by 2 times f of a plus 2 times f of a plus b plus f of b. We can do 3 segments, 4 segments, n segments. If you do one more time for 3 segments, you will start seeing the pattern. Maybe some of you already have seen the pattern, how to generalize this to n segments. Okay, so I want you to now try the same problem. Do this into 3 segments. We'll call it J1, J2, J3. Can you please try? You will see where this is going. So we applied the trapezoidal rule twice and got a formula. Now I'm asking you to write J equal to A to B f of x dx, and I'll write it J1 plus J2 plus J3. J1 being A, what is 1/3 of away from 1/3 of the distance? The total distance is b minus a divided by 3. That is 1/3 will be b minus a divided by, I'm sorry, I have to write a plus b minus a divided by 3 f of x dx, which is half b minus a divided by 3, and I have f of a plus f of, what is this? B plus 2a, or 2a plus b divided by 3. That is J1, first segment. J2,
Wait. Wouldn't the first point still be b minus a over 3, where you have 2a plus b over 3?
so I have a. What is a plus b minus a over 3?
Oh, okay.
So for clarity, let me redraw this. I have the segment A to B, and I have to chop this into 3 slices or 3 segments. The first segment will be 2a plus b over 3. Second segment will be, so I have 2a plus b over 3 plus b minus a over 3, which is a plus 2b over 3, and then I have b.
The integral was bringing the 3 minus there.
Yep. Yeah, you have the total length. You are dividing that into 3 equal segments. So it would be b minus a over 3 all along. So what is J2 then? J2 is 2a plus b over 3 to a plus 2b over 3 f of x dx, which according to trapezoidal rule is half of b minus a over 3. I have f of 2a plus b over 3 plus, sorry, f of 2a plus b over 3 plus f of a plus 2b over 3. Yes.
On the first equation, the J1, why would the top of the interval just be a plus b?
You mean this one?
Yeah,
I just took the starting point and I added the width of the segment. If you want, I can rewrite this as 2a plus b over 3. So you can similarly do J3. Well, I'll redraw this here. A, B, 2a plus b over 3, a plus 2b over 3, and each segment is b minus a over 3. So now let's do J3. Okay, I'm going to intentionally skip this integral and just write this, which is half of b minus a over 3. I have f of a plus 2b over 3 plus f of b. So the complete value would be just like we did I1 plus I2, we have to do J1 plus J2 plus J3, okay? And let me write it here for the sake of completeness. J equal to 1/2 of b minus a over 3. I have f of a plus 2 times f of 2a plus b over 3 plus 2 times f of a plus 2b over 3 plus f of b. So this is when you use 3 segments, okay? So I'm going to generalize this for n segments and spare us the derivation and just skip ahead to the formula. And if you are implementing it on a programming, if you are implementing it on the computer, you would use the n segment formula. If you are doing this for the exam, I will tell you how many segments to use, or I'll give you some kind of suggestion that is practical. Okay, you can't do 100 segments in the exam manually. Okay, but the problem could be like given to you, like you might be given a working code which I developed. You might have to use the code to vary some parameter in the code and answer a question or fill out a table, something like that. You will either be asked to do very few segments or given a code that already does the coding, the main multiple segments and answer questions. Okay. All right. So this is the formula for n segments. So trapezoidal rule applied over n segments in an interval a to b. Your goal is still to calculate integral a to b f of x dx, and that is approximated by b minus a, that is the total width of the interval, divided by 2n, where n is the number of segments, 2n, multiplied by f of a plus 2 times I equal to 1 to n minus 1 f of xi plus f of b. Where xi equal to a plus I times b minus a over n. So I equal to 1. Yeah. Yeah, that makes sense. So you are taking an interval A to B and dividing that into x1, x2, x3, xn minus 1. So you have how many segments? 1, 2, you have n minus n segments. Apply this for yeah, you have n segments. Okay, so this is the formula we are going to do using Excel shortening. Okay, and then the error associated with this formula, that is the error estimate. How would you do that? The error estimate, error total is minus b minus a whole cube divided by 12 n cube, 12 n cube multiplied by I equal to 1 to n summation second derivative of zeta I, okay, where zeta I is contained between xi and xi plus 1. That is, you are allowed to pick any value for zeta I in this interval, because what you are getting from this is an error estimate and not an absolute value of the error. So by the word estimate, what we mean is it differs from person to person, from choice to choice. So before we go on to Excel, I want to distinguish between two cases. So if you have f of x, one way of specifying f of x is to specify it analytically. That is, they can give you f of x to be a functional form, say for example 1 over 1 plus x squared plus 4x cubed something. They can give you a function using which we can compute the error estimates analytically. What is the other way of presenting a function, which we have been seeing in this course all along? Graphically or tabulate. Basically, you tabulate the function, tabulation or a graph where you get x and f of x as a table. Okay, and then you have to do integration at whatever interval that is provided to you. So in that case, the quality of the integration could differ considerably because it is limited by the resolution with which the data is provided. Okay, so we'll see examples of both. We're going to start with this. That is, I'm going to give you several functions, and you're going to carry out integration or develop a program in Excel to do the integration, and we'll see how that works. Okay, give you a minute to write everything up, and if there are questions, please ask. Yes. Can you come again? Yeah, plus 4x cubed. That's something like an example I made up. Yeah.
Zeta's just completely arbitrary. Or
What is completely arbitrary?
is zeta arbitrary? Would you be given that this question of that?
You are allowed to pick it. You have to pick it within that interval. So if you are dividing an interval into say 4 segments, you can pick a value of zeta. Suppose this value is 0.1 and this is 0.2. You can pick any value between 0.1 and 0.2 for zeta to estimate your error. So you can pick 0.15, you can pick 0.18, that's okay. It's like saying what is the nominal value of the error in this interval. So if you have your computer, please open Excel and we'll start, okay? Oh,
Yeah. We have 5 minutes.
okay, that's okay. I postponed the exam by a day, so which gives us one more lecture to do examples. Now, let me pause my recording here.